we start our part 2 for today's lesson, remember that you have your test. You also are receiving a couple worksheets. We're going to work through one of the worksheets in class, and then you'll have a little bit of it to finish, but you'll finish that up. But there's a second worksheet that you want to fill out and send. Actually, you don't send it. It's on kinetic energy, and what you want to do, it's a problem set 1. You'll see it, and you fill that out. Remember to use your equations for potential energy and for kinetic energy. So you want to work those out, show each step, and show all your work. Then you want to circle your answer so I can see your answer. Make sure you have the units for kinetic energy, okay, and for potential energy. So look back in your notes. You can use your notes, work on it, and you want to put that in your student file, your folder. And then we're going to collect the folders on May 19th. That's a couple weeks from now, actually about 10 days from now. And we'll collect those at Hoffmantown, and that's the day that you will pick up your exam. And then the exams will be completed at home. We're doing that because we have this corona problem, and so you'll finish those at home, and then you'll bring them back on the 26th of May. And of course, I'll have all of that written out for you. And so I want you to be sure to, this week, take some time as well to study your notes from this semester, and you'll do better on your exam if you study this week and begin preparing for that as well, so that the exam is still off a ways. It's a couple weeks from now, but you want to be studying. And remember, all the notes this semester are fair game on the exam. So let's look at a couple things that we saw last week. Last week we said that there was the law of moments. And the law of moments is the kind of the rule. It's the law that governs a teeter-totter. A teeter-totter, as we learned last week, is really a lever. It has a fulcrum in the middle. I'm going to label it with an F. And then it has a weight on one end. We think of people jumping up and down, but if you take that weight, and this is the weight 1, times the distance from weight 1 over to the fulcrum, that's the D1. So weight 1 times D1 is going to be equal to weight 2, I say this is a smaller weight, and the distance from that smaller weight to the fulcrum is D2. So we have weight 2 and we have D2. We multiply those together. D1 times W1 is equal to W2 times D2. So let's kind of work one of those problems. Let's say that we have a 50 Newton weight here on the left side, and it is 10 meters. That's the distance. So we'd say we have 50 newtons times 10 meters. That's going to be equal to the weight on the right side times the distance between the weight and the fulcrum. So let's say this weight over here is 40 newtons. So it's balanced. The question is, what is this distance then? If it's, we know that one side of the equation equals the other side of the equation. So the weight here is be 40 newtons times D2. And that's what we're looking for. We want to know how far should that weight be placed so that it balances. Now, you can kind of look at this, and if this is a heavier weight on the left side, 50, and it's 10 meters, you know that the lighter weight is going to have to be placed out further than 10 meters, because 40 times this D2 is going to be equal to 500. So we have 500 Newton meters is equal to 40 newtons times D2. Okay? And of course we know how to solve that. To get rid of the 40, we divide this side by 40 newtons, and these two cancel, so we're left with D2. But whatever we do to one side of the equation, we have to do to the other side. So we have to divide this side, the left side, by 40 newtons. And so the newtons cancel. I'm left with meters. And so I'm going to have something meters. So I've got 500 divided by 40. If I do the math on that, which I don't have my calculator with me, let me see if I can grab one real quick. So when I make this division, 500 divided by 40 is 12.5. So D2 is 12.5 meters. So it's further out. The 40 is further out, and this distance is 12.5. So that's what you want when you figure it out. You want to do it step by step, just like I've done, and then you show your answer. Remember the units. Don't forget units, it's meters, and circle your answer, okay? So we were looking at those kind of things last week. So what you want to do is you want to work a couple problems, make sure you can step through and work the same kind of problem. Now, let's say we have a different problem using a first class lever, a lever. And let's just say that we've got now, of course, our equation is W1 times D1 is equal to W2 times D2. Okay, so let's put our lever out here. Here's our fulcrum. Here's our pivot point. And we're going to put a 50-pound weight right here. Not 50 pound, 50 newton weight right there. And it's going to be 2 meters. So the distance is 2 meters. Okay, now we've got a 25 newton weight on the right side. And of course the question is, what is D2? So now you know that that smaller weight is going to have to be placed out further, isn't it? We're going to have to put it out somewhere out here for the smaller weight, 25 newtons, to balance with this larger weight. So let's go ahead and let's work it out. And so we have W1 times D1 is equal to W2 times D2. W1 is 50 newtons times the distance, 2 meters. It's going to be equal to the weight, which is 25 newtons on the right side, times D2. That's our question. D2 is the big question. What's that? Okay, so D2 is going to be equal to 50 times 2 is 100 Newton meters. Okay, is D2 times W2. So to get rid of the W2, the 25 newtons, we divide that. Okay, so let's show that 25 newtons. We divide that whole side by 25 newtons. But whatever we do to one side, we have to do it to the other side. Okay, so this 25 newtons cancels. It's really like 1 over 1 or 4 over 4. It's the same as multiplying by 1. So we just cancel it out, and we are left with W2 on that side. Now 100 divided by 25 is 4. The newtons cancel, and we're left with 4 meters. And that's what we're looking for. We want meters. And so 4 times 25 over here on the right side is equal to 2 times 50 on the left side. So yeah, 4 works. 4 meters is our answer. So be sure that you use your units and that you circle your answer. Okay, let's review some first-class levers then. A first-class lever, there's lots of levers, they function as levers, is a good one where it always has the fulcrum or the pivot in the middle. So you have a effort on one side and a resistance on the other. Okay, so a good example would be scissors. And here we've got let's see if we can show that to you here. We've got these are not really good looking scissors, but there's a pivot here. There's a screw right in the middle, so that would be your fulcrum. Here's your effort on the left, and your resistance is the paper that you're cutting through. That's the resistance. Okay, so there's a good example of a first-class lever. And let's go to second class now. Second-class lever, again, has fulcrum. It also has resistance, and it has effort. But here's the thing about a second-class lever is it has the resistance in the middle. Okay. So an example of that would be a fulcrum on one end. Here's resistance, and I pick it up, my effort. A wheelbarrow. So a wheelbarrow puts this load of rock in the middle. That's my resistance. And then it has the fulcrum or the pivot where the wheel is. And I pick up the handle and move it. So a second class lever would be like that. Now, so in other words, it has the resistance in the middle. Now, another really good example would be a, say some, like a nutcracker. Here's this big, long metal tubing, and it's got a little pivot, little screw on the end, and you put your nut right here, and of course your effort is going to come down and break the nut. The nut's going to be in the middle, so this is your pivot, your fulcrum, okay? So there'd be a nutcracker. Let's look at our third class lever. Sure hope you learn these, because these are on that test coming up this week. So here's the third class. Third class lever has the effort in the middle. So what would that look like if we put the effort? Well, if we if we take something that like tweezers. Here's some tweezers. Here's the let's say you're going to pick up something with the tweezers. So you pinch it here in the middle with your fingers. That's the effort. The resistance is what it grips. It's the object that it grips. And then down here would be your pivot, your fulcrum. Okay, so you have tweezers. Okay, you'd also have something like a broom if you put a broom. Let's see if that really is true. Here's the brush end of the broom that has and so this would be the dirt that you're pushing around. That would be your resistance down here. And then you've got one hand that you hold at the top of the broom, and you've got a second hand, and the second hand swings the broom back and forth. So the pivot really ends up being up here at the top. It's not like a screw, but you kind of you hold your hand rather steady at the top so that the broom pivots underneath. And then, of course, the other hand would be the effort, and it's pushing the middle of the broom around. So a broom would be a third class. So how is an easy way to remember that? First class, second class, third class. With the first class lever, the fulcrum is in the middle. The second class, the resistance is in the middle. And the third class, the effort is in the middle. Look at that, free. So if you can remember the acronym FREE, which shouldn't be too hard, you know that the fulcrum is in the middle for the first class. So that means the resistance and effort are on the ends. The resistance in the middle for the second class and the effort in the middle on the third class. So if you can keep that straight, that'll help you a lot. That really will. Okay. So let's move on. Let's go ahead and take a look. Let me ask you a little bit further with this first class lever. And of course, we're going to kind of put this fulcrum, and here's a rock. Let's say this rock is 50 newtons, and it is located 2 meters from the fulcrum, okay? 2 meters there. So what kind of force would you have to hit, and where would you have to hit it, okay, to make that rock catapult off, to spring it off of there? Okay, so let's say that you weigh 100 newtons, okay? Okay, and where would be the closest that you could be to the fulcrum and still knock that rock? Okay, well, we call that the effort arm. That's what this left side is called, the effort arm. And the right side is called the resistance arm. And it's done similarly to what we saw before. We use the equation effort times distance is going to be equal to the resistance times distance. Okay, so the resistance times the distance is 50 newtons times 2 meters. And then over here we have, we wonder what the distance is going to be, so let's put that as our variable. And we know what our effort is. Our effort is going to be this guy who's 100 newtons is going to jump. Where does he need to jump? So we can do the math on this, and as you can certainly see, it's not too hard to see that 100 Newton meters is what this right side figures out to be. And then according to get the D, of course, to get the D by itself, I have to divide by 100 newtons. And then I divide by 100 newtons on the other side. These two cancel. I'm left with D. 100 over 100 is the same as 1. And of course, newtons cancel. I'm left with meters. That's what I want. I want to know, my answer has to be in meters. And my answer is going to be that if I drop 100 Newton effort, it needs to be 1 meter from the fulcrum. Now if it's out further, if it's out here like 5 meters, well, obviously I'm going to have a mechanical advantage there. I'm going to have a powerful lever. It's going to shoot that rock even further. But the minimum has to be 1 meter. So I'm going to have to push my effort down. My effort's going to have to hit at least 1 meter here from that fulcrum. So, interesting, we can use this for problems. Now, let's talk about this mechanical advantage. Mechanical advantage. And of course, your book goes into that. This is new stuff now. This is actually new notes here. And they use the expression MA for mechanical advantage. Well, mechanical advantage is really a measurement of the, and we could just say it measures the, quote, free or force multiplying ability of a machine or a lever. Remember, a machine does work, a lever will do work as well, so a lever is a type of machine. So, what kind of force multiplying ability do we have? They would call that the mechanical advantage, okay? So usually what you want to do is, let's say that in this upper equation here, you've got, or this last example that we just did, we are throwing this 50 Newton rock, okay? And so if we put the mechanical advantage and try to figure that out, we need to know what is the resistance moved divided by the effort and in this case 50 newtons. It's a mechanical advantage. 50 is my resistance that was moved. I'm going to divide that by the effort, and of course the effort was 100 newtons. So 50 divided by 100 is 1/2, right? That's going to be the mechanical advantage of 1/2. That's not very much. In fact, if I moved my 100 Newton effort out 10 more meters, instead of having it 1 meter wide, I put it at 11. I would really have a much higher mechanical advantage, okay? So that's one way of deciding. Let's look at another example here as we move ahead. We're going to go to number 3, or part 3.